In this video, we're going to go over section 4.4, where we're going to look at the final version of our graphing strategy. So we're going to bring together everything that we've seen in the last several sections, as well as what we learned about asymptotes in section 2.2. So here's the procedure for curve sketching, the final version. So the first thing we're going to do is analyze our function. So we're going to find the domain and intercepts as well as the asymptotes. Then we're going to analyze our derivative. So we're going to find the partition numbers for our derivative and the critical numbers for our function. Then construct a sign chart for our derivative, and then determine the intervals that our function is going to be increasing and decreasing, as well as any local extrema that f may have. Then the third step, we're going to do the same thing by analyzing our second derivative. So this will tell us the intervals on which our function is going to be concave upward or downward, and as well as the inflection points of our function. And lastly, what we'll do is we'll bring all of that information together to sketch the graph of our function. So let's look at this example here. We want to use this final version of our graphing strategy to analyze this function here. So we'll do this using this step-by-step procedure up here. So the first thing we're going to do is analyze, step one, we're going to analyze our function. Okay. So we're going to find the domain, the intercepts, and the asymptotes. So notice, looking at our domain first, when the denominator of this rational function is equal to 0, our function is going to be undefined. Okay, so for x is equal to 1, f of x is undefined. So this tells us the domain of this function is going to be all real numbers except for when x is equal to 1. So negative infinity up to 1, and 1 to infinity. All right, now we want to find our intercepts. So to find our x-intercept, we set our function equal to 0. So then we'll get that 2x is equal to 0, so this tells us that x is equal to 0. So our x-intercept is going to be the origin. Similarly, we want to find our y-intercept. So we're going to plug in 0 into our function. All right, and in this case, we'll get 0. So this tells us that our y-intercept is also the origin. All right. Now we're going to want to find the asymptotes of our function. And remember, we're going to be using the strategies that we learned in section 2.2. So we know that the vertical asymptote is going to occur when our function is undefined. And we just showed above that that happens when x is equal to 0. So we're going to have a vertical asymptote when x is equal to 1. Okay? Because this will make our function undefined. All right. Now, when we have a rational function, we saw in section 2.2 that we'll need to factor out the highest degree term of its numerator and denominator, and then evaluate the limits at infinity and negative infinity. So what I mean is, we have f of x is equal to 2x over 1 minus x. And if we want to factor out the highest degree term, or the leading term, out of the numerator and denominator, that looks like the following. So the highest degree term in the numerator is 2x, and in the denominator, it's minus x here. So we'll plot on minus x, and what we're left with is 1 over minus x plus 1. Okay. When this minus x redistributes to these terms, we should get 1 minus x here. All right. So then we get 2x over minus x times 1 over minus 1 over x plus 1. All right. Simplifying this a little further, we'll get 2 times this guy. All right, so after factoring out the highest degree term from the numerator and denominator, we now want to evaluate the limits at infinity and negative infinity. So we'll look at the limit of this guy here as x goes to infinity. So what we'll get here is negative 2 stays there, and we'll have 1 over this here. All right. Now remember, if we have a fraction of this form, as the denominator gets bigger and bigger, this whole thing is going to get smaller and smaller. So this guy is getting closer and closer to 0. So we end up with this here. All right, so that'll be negative 2 times 1, so we'll get negative 2 here. Similarly, if we want to look at the limit of our function as x approaches negative infinity, we'll do the same thing here. And by the same reasoning, this guy is going to get smaller and smaller. It's going to get closer and closer to 0. And so we see that the limit of our function as x approaches negative infinity is also negative 2. And since these limits are equal to each other, this tells us that we'll have a horizontal asymptote at y is equal to negative 2. However, in this chapter, we're going to use this theorem here that we saw from section 2.2 to determine the horizontal asymptotes of a rational function. So this is the theorem here, and it says if we have a rational function of this form, and we have our leading terms here, a,m, and bn, where they're non-zero, then the limit of our function as x goes to infinity is actually just going to be the limit of our leading terms as x goes to infinity. And similarly, the limit of our function as x goes to negative infinity is going to be the limit of our leading terms here as x goes to negative infinity. Okay? And there are going to be 3 possible cases for these limits, and they're based off of the degree of our leading terms. Right, so this m and n here are the degrees of our variables x here. So if m is less than n, then we'll have that the line y is equal to 0 is going to be our horizontal asymptote. If these degrees are equal, then we'll see that this line here, which just looks at the coefficients of our leading terms, is going to be our horizontal asymptote. And then if m is greater than n, then in this case our function will not have a horizontal asymptote. Okay? So we can just use this theorem to determine our horizontal asymptotes. And in this particular example, looking back at our leading terms here, we saw that we factored them out of our numerator and denominator here. And so our leading terms were 2x over minus x here. And so looking at the degrees of these guys, we have 2x to the power 1 and minus x to the power 1. So in this case, our degrees of our leading terms are equal. So we have this second case here, where m is equal to n. And in this case, the line y here is going to be our horizontal asymptote. So that's going to be the coefficient of our leading term in the numerator, which is 2, over the coefficient of our leading term in the denominator, which is negative 1. Okay? So doing that, we will see that we get a horizontal asymptote at y is equal to negative 2 here, which is what we got doing this here. All right, now let's do step 2 of our graphing strategy. So in that case, we're going to analyze our derivative. So the derivative of our function, we have a rational function here. What we can do is we can rewrite this with positive exponents, and Yeah, we can rewrite this with positive exponents and use our product rule. In this case, I'm just going to use our quotient rule. So remember, that's going to be our g on the bottom, then the derivative of our function on the top, minus our function on the top times the derivative of our function on the bottom. And that'll be all over our function on the bottom squared. Now just multiplying these, we'll get 2 minus 2x, and then we'll get plus 2x here. So the minus 2x and the plus 2x will cancel. And so we'll get 2 over 1 minus x squared. And so we want to find the partition numbers for our derivative. I'm going to abbreviate it like this. And so we know that our partition numbers are where our derivative's either going to be undefined or equal to 0. In this case, this will never be equal to 0. So our only partition number occurs when this is going to be undefined. And we know that this will be undefined if we're going to divide by 0. So we want to figure out when 1 minus x squared will be equal to 0, and that'll occur when x is equal to 1. So this tells us our partition numbers are x is equal to 1. Right? Then we also want to find our critical numbers, I'll abbreviate like that, of our function. So this would be the partition numbers of our derivative. And we also want to find the critical numbers of our function. Alright, so in this case, we do not have any critical numbers, because remember, the critical numbers of our function have to be in the domain of our function. And we saw up here that the domain of our function is all numbers except 1. So that means this partition number, x is equal to 1, is not in our domain. Alright. So our partition number here breaks our interval, or breaks our domain up into these intervals. So we'll look at negative infinity up to 1, and then 1 to positive infinity. So what we want to do is construct this sign chart. So we'll look at the value of our derivative in these intervals. So we'll evaluate our derivative at 0. Plugging this into our derivative, we'll get 2, which is positive. So over this interval, our derivative is positive, and this tells us our function is increasing. We also know that our derivative is going to be undefined at 1, so we'll write that there. Right, now we want to find the sign in this interval. So we'll look at our derivative evaluated at 2. So plugging this into our function, this is a negative number here, but it's squared, so this will be a positive number. Okay. So our function is going to be increasing. So we can conclude that our function is increasing from negative infinity up to 1, and then 1 to infinity. And we can also conclude that we have no local extrema, right? Since in order to have a local maximum or minimum here, f of x would go from increasing to decreasing or vice versa at this point. And since we're not changing we're not going from increasing to decreasing or vice versa, we don't have any local extrema here. All right. Now we're going to do step 3, where we want to analyze our second derivative. So we saw from above that our first derivative was this here. And in this case, I will use the product rule. So I'll rewrite this guy like this here. And then we'll take the derivative of that. So we'll have 2 times the derivative of our outside function. We're going to have to use chain rule. So this negative 2 is going to come down. It's going to be evaluated at our inside function. And then our exponent is going to be -2 minus 1, so we'll get -3 here. And then we still have to multiply by the derivative of our inside function, and that is -1. Okay. So multiplying this out, we'll get -4 times 1 minus x to the -3 times -1. So this just ends up being +4. Okay. And then we can rewrite this with positive exponents as this here. All right. So the partition numbers of our derivative, our second derivative, are just going to occur when this is either equal to 0 or undefined. And like we saw when looking at the partition numbers for our first derivative, a rational function of this form will not be equal to 0, but we want to see when this will be undefined, and we know that'll happen when our denominator is equal to 0, or in other words, when x is equal to 1. Alright, so we want to construct a sign chart for our second derivative, breaking our domain up into these intervals here. So we want to evaluate the sign of our second derivative, because the sign of this guy will tell us if our derivative is going to be concave up or concave down. Sorry, if our function is going to be concave up or concave down. Alright, so we'll evaluate our derivative at 0, our second derivative. Plugging this into our second derivative here, we'll get 4, so this will be positive. So our function is going to be concave up over that interval. We again know that our second derivative is undefined at x is equal to 1, so we're just going to put that there. And then we want to see the sign of our second derivative in this interval. So we'll evaluate it at 2. In that case, we'll get 4 over 1 minus 2 cubed. So we'll get 4 over -1, so this will be negative. So in this region, our function is going to be concave up. Alright. Something else to know here is that our function is going to be, we're not going to have an inflection point here. Sorry, this should be concave down. Since our second derivative is negative in this region, our function is going to be concave down. Now, something to note here is that our function is not defined when x is equal to 1, right? We said that our domain is all real numbers except for x is equal to 1. So you might normally think that we'll have an inflection point here since we're going from concave up to concave down, but since we're not defined at this point, we do not have an inflection point. All right. And then the last step for our graphing strategy is to actually sketch the graph of this guy. So the first thing I will do is draw our asymptotes. So we said we had a vertical asymptote at x is equal to 1. And we also have a horizontal asymptote at x is equal to -2. Okay. All right. Then what we're going to do is make note of any extrema or inflection points. And we know in this example we don't have any. So next thing we'll do is make note of our x and y intercept. And we know that occurred at the origin here. Okay. We also know that in this region, our function is going to be concave up and increasing. Okay. So it's going to be concave up, so of this sort of shape here, but we know that it has to be increasing. So we're not going to have this region where anything's decreasing like that. So it'll kind of maybe be more like this. Especially since we know that we have to intersect this line and we can't cross this asymptote or this one. This gives us an idea that our function is going to look like this. Similarly, in this region here, we know from 1 to infinity, our function is going to be concave down and increasing. All right. So concave down kind of looks like this, but remember we're going to be increasing the whole time, so we're not going to have this portion. It's going to kind of look more like this. And we know that we can't cross the asymptotes, so our function is going to look something like that. And then once we have an idea of our function, we can also just plot these points here, and so we can be a little more accurate with the sketch. So we know when x is equal to -1, our output's going to be -1. So we have a point there. We also know when x is equal to 1/2, our output's going to be 2, so we have a point there. So our function is going to intersect those guys and look something like this. Then we know when x is equal to 2, our output's going to be -4. And when x is equal to 3, it'll be -3. Okay? So our function is going to look something like this, and never crossing the asymptotes. Alright, so let's look at another example here. We're going to do the same thing now for this function here, h of x. So we know the first thing we want to do is analyze our function. So first we will find the domain of our function. Looking at this rational function here, we know that this guy is going to be undefined when x is equal to 0. So this tells us that our domain is going to be all real numbers except for x is equal to 0. Next thing we want to do is find our intercepts. We know that our x-intercept is going to occur when h of x is equal to 0. So we can multiply by x squared on both sides to cancel these. So multiply by x squared. So then we're left with 4x plus 3 is just equal to 0, since 0 times x squared is going to be 0. And then solving for x, we'll subtract 3 on both sides and then divide by 4. So we get x is equal to -3/4. So this tells us our x-intercept is going to occur at this point here. And then to find our y-intercept, we're going to plug in x into our equation. Sorry, we're going to plug in 0 into our equation. And we know that this is undefined because we can't divide by 0. So we don't have a y-intercept. Alright, next thing we want to do is find the asymptotes. Alright, and so like I said in the last example, we're going to use this theorem here to help us instead of doing this process here. But you can do either process. You'll end up with the same answer like we saw for this guy. So in our case here, going back to our function, we're going to look at our leading terms here. So we have our leading term is 4x in the numerator, and then the denominator is x squared. And so the degree of this variable here is 1, and this one is 2. Okay? So that tells us that the degree of the leading term in our numerator is m, and our denominator is n. And we saw that m was 1 and n was 2 in that case, so m is less than n. So in this case, we're going to have a horizontal asymptote at the line y is equal to 0. Okay? So we'll write this out by theorem 4 from section 2.2. We're going to have a horizontal asymptote at y is equal to 0. Alright, and then we know that our function is going to be undefined at x is equal to 0. We're going to have a vertical asymptote here. So vertical asymptote at x is equal to 0. just want to highlight this stuff so it's easy to keep track of when we go back through to get all the information to graph it. All right, now step 2, we're going to analyze our derivative. So in this case, I'm going to use the quotient rule again. So we'll have our bottom function times the derivative of our top function minus our top function times the derivative of our bottom function all over our bottom function squared. Okay. So simplifying this a little bit, multiplying these guys, we'll get that there. So we can combine these terms. So we'll get negative 4x squared minus 6x all over, sorry, this should be x to the power 4. Alright, and then taking out an x from every single term here, we'll get minus 4x minus 6 over x cubed. Alright, and then we can simplify this a little further by pulling out a minus 2. So we're left with this guy. Alright, so that is our derivative. We want to find the partition numbers of this guy. So first we know that our derivative is going to be undefined when x is equal to 0, so we can't divide by 0. So that is one of our partition numbers. And then the next one will occur when this guy is equal to 0. So when this is equal to 0, alright, because we know that in order for this to be equal to 0, this top function, so our numerator, needs to be equal to 0. So solving for x here, we can divide by negative 2 on both sides, and so this side will stay 0. So we're just looking at 2x plus 3, and when that'll be equal to 0. And we can find this by solving for x, so we'll subtract 3 on both sides and then divide by 2 on both sides. So we get this here. We also want to find the critical numbers for h of x. And so remember, that's going to be the partition numbers of these guys that are in the domain of h of x. And so we know that this guy is going to be our only critical number. Since our partition number for the derivative of h of x is x is equal to 0, but we know that 0 is not in our domain of h of x. So it can't be a critical number. Alright, so now we'll construct our sign chart to find the intervals of increasing and decreasing for our function. Move this up a little bit. Alright, so our intervals are going to be broken up by our partition numbers. Alright, so to determine the sign of our derivative in these intervals, we'll evaluate our derivatives at numbers within these intervals. So the first one we'll look at is negative 2. Plugging this into our derivative, we get this here, and this will be a negative number. So we know that our function is going to be decreasing over this interval. We also know that our derivative is equal to 0 at negative 3 over 2, so we'll put that there. Looking at the next interval, we'll evaluate our derivative at negative 1. And then evaluating this, we'll get a positive number here. So our function is going to be increasing over that interval. And then something to note here is that we see that our function goes from decreasing to increasing. So this means at this point, we're going to see a local minimum. And then we also want to see the sign of our derivative over this interval. So we'll evaluate it at 1. And we'll get a negative number here. So our function is also decreasing on that interval. And then we also know that our derivative at x is equal to 0 is undefined. And we saw that x is equal to 0 is also undefined for our function h of x. So we won't have any extrema at that point either. All right, so we can conclude that our function is increasing on this interval here and decreasing on these two. Right? And then we also know that we have a local minimum at x is equal to negative 3 over 2. All right, and then for step 3, we want to analyze the second derivative. So we'll do quotient rule again. All over our bottom function squared. All right, so we'll get this on the top here. And then x to the 6th power on the bottom. All right, so then we'll end up with x to the 6th on the bottom here. All right, so we can take out 2 x's from all of these terms. And then we can simplify this a little further by pulling out a factor of 2 from these terms on the top. All right, and then we want to find the partition numbers for our second derivative. And we know that this is going to happen when this is undefined or equal to 0, and this is undefined when x is equal to 0. So that's one of them, and then we also want to figure out when this whole thing is equal to 0, and that'll happen when our numerator is equal to 0. So then solving for x, we'll divide by 2 on both sides, so we'll still get 4x plus 9 is equal to 0. And then solving for x, we'll subtract 9 on both sides and then divide by 4. So we'll get negative 9 over 4. All right. So we'll look at the sign of our second derivative over the following intervals. Because our partition number breaks our domain up into these intervals. All right, so we'll evaluate our second derivative at numbers within these intervals. So first we'll look at negative 3. All right, so we'll get a negative number here. So over this interval, our function is going to be concave down. We know at this point our derivative is going to be equal to 0, so we'll put that there. Then we want to look at the value or the sign of our derivative over this interval. So we'll evaluate our second derivative at -2 here. So this will be positive. So our function is going to be concave up over this interval. And then we know that since our derivative changes sign from minus to positive here, our function is going from concave down to concave up. So this tells us that we're going to have an inflection point when x is equal to -9/4. And then we still want to find the sign of our second derivative over this interval. So we'll evaluate it at x is equal to 1. And we can see that'll be positive. So we're still concave up over this interval. Okay. And then we also know that we're going to have our derivative and our function is going to be undefined when x is equal to 0. All right. So the first thing we'll do is plot our asymptotes and our x and y intercepts. So we know from step 1 that we have a vertical asymptote at y is equal to 0, vertical asymptote at x is equal to 0 and a horizontal one at y is equal to 0. We also know that we don't have any y-intercepts, but we do have this x-intercept here. So we'll plot that. So we have our asymptotes here. Then we have our x-intercept at -3/4, 0. So that'll be roughly here. Right? We also know that our function is going to be concave down over this interval and then concave up over this one. And that our function is going to be decreasing over this interval here, increasing over this one, and then decreasing for the remainder. So our function is going to be decreasing, so kind of like this, up until we get to this point here, and then it's going to start increasing. And then we can't cross this asymptote here. And then similarly, from 0 to infinity, we saw that our function is going to be decreasing. And it'll be concave up. So decreasing concave up is going to be something like this here. All right, and then we can plot a bunch of points here to help us get a better shape of this graph. So plotting these guys here, we have -7, 0, -0.5, so that'll be this point here. -3, -1. 0.5 there. -3, -1. -9/4 we saw would be our inflection point, and it occurs at this point here. So somewhere about there. Then we also have -1/2, we're going to get 4. And then we skipped this one, we have -1.5, -1.33. Somewhere around there. So it looks like our function looks like this here. Alright. And that makes sense here. It looks like our function is decreasing over this region and then increases here. And then it looks like our concavity changes at this point as well. Right, and then we know that over this interval from 0 to infinity, our graph is going to behave somewhat like this. And so plotting these points will give us a better idea of that. So we have 1.5, 4. At 1, we get 7. And at 8, we get 0.5. So our function is going to be decreasing and concave up and intersect these points here. All right. There are also a couple examples in the textbook of graphing a log function in this way that I do recommend that you take a look at. In those examples, we use the same approach. You just need to be a little careful with the domain. So like, for example, the natural log function is only defined for numbers greater than 0. Okay, so take a look at that when you have the chance. The last example we're going to look at is modeling an average cost function. But first, we're going to introduce this new definition of an oblique asymptote. So if a graph approaches a line that is neither horizontal nor vertical as x approaches positive or negative infinity, then that line is called an oblique asymptote. Okay, so we'll see an example of that in this problem here. So we're given the cost function c of x here, where x is the number of items produced. And what we want to do is use the graphing strategy to analyze the graph of the average cost function. And if you remember from section 2.7, I believe, the average cost function is denoted by this here. So c of x with a bar over it, and it's going to be equal to our cost function over the number of items produced. Okay. So we want to use the graphing strategy to graph that guy, as well as graph the marginal cost function on the same set of coordinate axes. And if you remember from that same section, the marginal cost function is going to be the derivative of our cost function. All right, so we'll just do the same thing that we did in the last several examples. So we're going to want to graph the average cost function, which is given by this here. Okay, so the first thing we're going to want to do to use our graphing strategy is analyze this guy here. So we're going to find the domain, the intercepts, and the asymptotes. So the first thing to note here is that our domain is going to be all positive real numbers. Right? Since x is going to be the number of items produced, we can't have negative items produced. We can have that we'll have 0 items produced. However, we can't have a division by 0 here. That would make this guy undefined. So our domain is going to be all positive real numbers. So from 0 to infinity. Now looking at the x-intercept, we'll find this by setting our function equal to 0 and solving for x. We know that this guy will be equal to 0 when our numerator is equal to 0. So we can just say that our function is going to be equal to 0 when this guy is going to be equal to 0. Right? However, when setting this equal to 0 and solving for x, we'll get imaginary numbers, and imaginary numbers are not in our domain. So in this case, we don't have any x-intercepts. Similarly, I'm going to find our y-intercept. We're going to look at plugging 0 into our function. And in this case, we're going to have a division by 0, which is undefined. So we also don't have any x-intercepts. All right. Now we're going to use theorem 4 here to see if we have any horizontal asymptotes. So we want to look at the degree of our leading term in the numerator and denominator of our function here. So our leading term in the numerator is going to be 0.25x squared, and in our denominator we just have x. And so the degree of this guy is 2. So going back to our theorem, that means our m is equal to 2. And the degree of this guy is 1, so that means our n is equal to 1. So this tells us that we have this case here where our m is greater than n. And in this case, this tells us that our function does not have a horizontal asymptote. So we can conclude no horizontal asymptote. And then we do know that we're going to have a vertical asymptote at x is equal to 0, since our function is undefined there. All right. Now lastly, we will have an oblique asymptote. And we can find this by, first we'll rewrite our function like this here. And we'll see why in a moment. But all we did was just simplify this, so taking out an x from this guy, and so we have 1600 over x plus 0.25x. All right, so looking at our average cost function here, note that as x gets bigger and bigger, so this means more items are being produced, we see that this guy here is going to get smaller and smaller. So this term is going to go to 0 as x goes to infinity or gets bigger and bigger. So this tells us that our average cost function is going to get closer and closer, or is going to equal this as x gets bigger and bigger. Okay? So with this information, we can conclude that we have an oblique asymptote at y is equal to 0.25x, right? Because you remember from earlier, we said if a graph approaches a line that is neither horizontal nor vertical as x approaches infinity or minus infinity, that line is called an oblique asymptote. And we can see as x gets closer and closer to infinity, we're approaching this line here, and this line is neither horizontal nor vertical. So we conclude that this line must be an oblique asymptote. And I believe we'll go into better methods to find the oblique asymptote, which will include polynomial long division. But for now, we're just going to use this way to show this in this example. All right. Now for step 2, we're going to analyze our derivative. So what I'll do is I'll rewrite this guy using negative exponents. So like this here. And so then taking the derivative of this guy, we'll use our product rule. Sorry, I said product rule, but I meant power rule. So we're bringing this down in front, and then we have x to the power negative 1 minus 1. So this becomes negative 1600 over x squared, writing this with positive exponents, plus 0.25. All right, now we want to look at the partition numbers of our derivative. And so that'll be a little bit easier if we rewrite this guy over a common denominator. So this would be 0.25x squared minus 1600 all over x squared. So our partition numbers of this guy, we know we're going to have x is equal to 0. Since we can't divide by 0, this guy will be undefined when x is equal to 0. But we also want to see when our derivative will be equal to 0. And so we know this is going to equal 0 when our numerator is equal to 0. So solving for x here, We're going to add 1600 to both sides, and then we'll divide by 0.25. And 1600 divided by 0.25 is going to be 6400. And then we'll take the square root of both sides, so we'll get plus or minus 80. Okay. But remember, our domain is going to be all positive real numbers, so negative 80 is not in our domain. So this tells us we're just going to take positive 80. So these are our partition numbers, x is equal to 0 and x is equal to 80. And then looking at our critical numbers of our function, this is going to be the partition numbers of our derivative that are in our domain. And remember, we said our domain is all positive real numbers, so that doesn't include 0. So x is equal to 0 is going to be our only critical number. Or sorry, x is equal to 80. Only critical number, since x is equal to 0 is not in our domain. Okay, so now we'll construct a sign chart. So our domain is going to be broken up into the following intervals based off of our partition number. Alright, so we'll look at the sign of our derivative in each of these intervals. So we'll pick a number in our first interval, so I'll pick 70. So plugging this into our derivative, looks like this here, and is going to be negative. So in this region, we know that our function is going to be decreasing. We also know that when x is equal to 80, our derivative is going to be 0. And we want to find the sign of our derivative in this region. So we'll evaluate it at 90 here. And plugging this into our derivative, same way we've been doing, we'll get a positive number. So in this interval, our function is going to be increasing. And since we're going from decreasing to increasing at this point, at x is equal to 80, we're going to have a local minimum. Okay? So this tells us our function is going to be decreasing on 0 to 80, and increasing on 80 to infinity. And then we're going to have a local minimum at x is equal to 80, and so plugging that into our function, we get 40. So our local minimum is going to be at that point. Okay, so for step 3, what we want to do is now analyze the second derivative. Okay. So for this one, we will use, we're going to take the derivative of this guy, so I think we'll just use quotient rule here. So we'll do the bottom function times the derivative of our top function. So that'll be 0.25, so we'll just use power rule. This 2 comes down in front, and we have 0.5 times x to the power 1 minus our top function times the derivative of our bottom function all over our bottom function squared. So simplifying this, we'll end up with 3200 over x cubed. So this is our second derivative here. Alright, and then something to notice about this function here is that this guy is actually always going to be positive, right? Because for all x in our domain, right, all positive numbers, our second derivative is going to be positive. The only thing that would make this guy negative is if we plug in a negative number in here, but that's not even in our domain. So we're to make a quick sign chart. What this tells us is from 0 to infinity, so over our whole domain, our second derivative is going to be positive, so this tells us our function is going to be concave up. Alright, so going back to our problem, we have everything we need to graph the average cost function, but we also want to find the marginal cost function and graph it on the same graph. So the marginal cost function is just going to be the derivative of this guy here. Okay, so we'll use power rule. So this 2 will come down in front, so we'll have 0.5 times x. So for our marginal cost, we'll take the derivative of just our cost function, not our average. So we get 0.25 times 2 times x, taking the derivative using power rule. So we get 0.5x. Okay? And this guy is actually going to be pretty easy to graph. This is just a line. So down here, I have the graph of our average cost function here, this blue curve, and then the graph of our marginal cost, which we said was just a line here. Okay. And so we can graph these by following the graphing strategy that we've been doing, but just in the interest of time, I've provided the graphs here. But we can follow that strategy for a minute. We know that our vertical asymptote can occur at x is equal to 0. We also know that we have an oblique asymptote, right, when y is equal to 0.25x, so this here. So we can do a rough sketch of that guy. And so that actually looks like this here. So we have this oblique asymptote, so this asymptote that's not horizontal or vertical. Like that there. We also saw that we had a local minimum at the point 80, 40 here. So looking at our graph, 80 is here and 40 is there. So at this point, this tells us that this is going to be our minimum average cost here. All right, and then using the intervals of increasing and decreasing and concavity that we saw using the graphing strategy, we would get a graph like this for our average cost. Okay. So conceptually, what this tells us is that the minimum average cost occurs when our average cost is equal to the marginal cost. Right? So we can see that using this graph here, where these two graphs intersect, our marginal cost and our average cost is our minimum value. So when these guys are equal, we have our minimum average cost. All right, so that'll be it for this video.